300 Linear Circuit Analysis 2, Module 3, Video 6, Bode's Method of Plotting the Frequency Response. In this video, we'll review the vector interpretation of frequency response. We'll review Bode plots. Then we'll look at Bode's method for plotting the frequency response. And then we'll summarize and look at upcoming attractions. So, the vector interpretation. We saw previously that the magnitude of h of j omega could be interpreted as the product of a scale factor, magnitude k, times the product of the length of the vectors from zeros to j omega, divided by the product of length of vectors from poles to j omega. We saw that the angle of h of j omega could be treated as the sum of the angle of k, the scale factor, which would be 0 or 180 degrees, plus the sum of the angles from the zeros to j omega, less the sum of the angles from the poles to j omega. So for instance, when you had a first order low pass system with a pole at minus alpha, when you're in the low frequency region and you're at j omega small, then the vector from the pole at minus alpha to j omega is approximately of length alpha and of angle 0. And that's this small region over here. This is with omega is at alpha of 1, or omega over alpha is what's plotted here. So for the low frequency region, you get a gain of 1, and it has a slope. Actually, the angle would be increasing with the omega here, so it comes out with a slope, a straight line coming out of omega equals 0. Then when you get to the frequency omega equals alpha, the corner frequency, the vector from the pole to the omega equals alpha is a straight line, and it's of length root 2 alpha, because you've got alpha on the horizontal, alpha on the vertical, so the length there is root 2 alpha. And so the gain is 1 over root 2, which is 0.707. The angle at that point is the angle from the pole to j omega is plus 45 degrees. And since you subtract the angle from the pole, that turns out as minus 45 degrees in the frequency response. And then for high frequencies, we're way out here, and the length of the vector is basically omega. So the gain rolls off like 1 over omega, as we see the gain plot doing here. And it approaches the vector from the pole to omega, j omega, approaches an angle of 90 degrees. And so the angle of the frequency response approaches minus 90 degrees. We can look at the first order high pass system the same way, except now there's a vector coming out of the 0 to the point omega, and we have the same vector coming out of the pole to the point omega. So for low frequencies, the vector from the 0 is growing proportional to omega. It's always length omega, and so it's growing proportional to omega, whereas the vector from the pole is not changing very much. So the gain increases with a linear proportion to omega. When you get to the corner frequency, the vector from the 0 has length omega. The vector from the pole has length root 2 alpha. They're both actually length alpha. The vector from the 0 is length alpha. The vector from the pole is root 2 alpha. And so the gain is 1 over root 2. And then for very high frequencies, the vector from the 0 has length omega. The vector from the pole has length omega, so the gain goes to 1. In the same way, the angle starts out at 90 degrees when the vector from the 0 is dominating things, goes to plus 45 degrees, so 90 degrees minus 45 degrees, and then it eventually ends up being 0 degrees for high frequencies. When you have an underdamped system with a poles at minus zeta omega naught plus minus j omega naught, that's an approximate solution to the denominator polynomial there, with a 0 at the origin. This is like the output of an RLC, series RLC across the resistor, driven by the voltage. Then, when you're at low frequencies, the 0 at the origin dominates, so you have proportional to omega growth in the magnitude. The angle, these two cancel each other out. The angle from the upper pole and the angle from the lower pole cancel each other out, add up to 0, so you just have the 90 degree angle coming out of the 0, determining the angle there. As you go around the resonant frequency, when you're zeta omega naught below to zeta omega above, when you're at zeta omega naught below the resonant frequency, the length of the vector from the upper pole there is root 2 zeta omega naught. Same when it's zeta omega naught above the resonant frequency. And then when you're at the resonant frequency, the length there is just zeta omega naught. And so you get this behavior where it goes through 1 over root 2, and then goes to a gain of 1, and then back down to a gain of 1 over root 2. And that's what defined the half-power bandwidth between these points where the gain was 1 over root 2, which is omega naught minus zeta omega naught and omega naught plus zeta omega naught. And in the same way, the angle curve starts at 90 degrees, goes through 45, 0, minus 45, and then goes to minus 90 degrees for high frequencies. And you can again see that in the vectors. For high frequencies, you've got 3 vectors, one from the pole, 0, and 1 from each of the poles, and you're the same distance away from all of them when you get far enough away. So the length, there's an extra 1 over omega in the denominator because you've got omega in the numerator and 1 over omega times 1 over omega, omega in the numerator, and then omega times omega in the denominator. So you get 1 over omega behavior in the gain, and the angle goes to 90, minus 90, minus 90, minus 90 degrees. For Bode plots, you plot the gain as the 20 log base 10 to the magnitude of hj omega, and you plot that versus frequency on a log scale, and you plot the angle versus frequency on a log scale. So that same low-pass first-order system where the gain, now we have a bigger, you can see more of the space where the frequency is small. And you can sort of see what small means here. Here's the corner frequency, and so small is more than 1 decade below the corner frequency. And that the approximation that the gain is 1 or 0 dB is perfectly good. And above the corner frequency, the gain rolls off at 20 dB per decade. And there's a correction there. You could actually draw straight line asymptotes that intersect the corner frequency with a correction of 3 dB. The angle curve is not quite as good of a match, but again, it goes 0 degrees for low frequencies, approximately a straight line between 1 decade below and 1 decade above the corner frequency, down to minus 90 degrees for 1 decade above. And again, you can see you sort of have to get an extra decade above and below to get into that better approximation range for those. So here's just the Bode plot for the high-pass filter, 20 dB per decade growth where the gain is proportional to omega, and then a gain of 0 dB where the ordinary gain is 1. Angle starts at 90 degrees, goes through minus 45, down to 0 degrees. For the resonant plot, we didn't look at this, and this hasn't been updated to the better form with the 2 zeta omega naughts replacing the 2 alphas. But again, you can see the same behavior when you put the Bode plot. You see the proportional to omega behavior has a gain of 20 dB per decade. The proportional to 1 over omega behavior has a gain of minus 20 dB per decade, decays at 20 dB per decade. The peak at 1 has a gain of 0, and you can see the 3 dB bandwidth would be between those 2 points, just 3 dB below the gain of 0 dB. You can see the 90 degree through the angle of 45, 0, and 45. And so you see it really steepens everything up a little bit. And you just see this does not fit the straight line asymptotes would intersect at 0 there, but you have this little extra peak there. Actually would not intersect at 0 there, and it depends on the degree of damping there. So we're not going to get into too much of this for Bode plots for bandpass, narrow band, or resonant systems, but we'll look at this one here. So, I mean, they're perfectly useful, but Bode's method that we're fixing to study doesn't really apply to them directly. So we've already seen that the magnitude curves can be approximated by straight lines. When the gain is decaying at 1 over omega, then you've got 20 log base 10 magnitude h of j omega decreases at minus 20 dB per decade. And then when it's growing at proportional to omega, then the gain in dB grows 20 dB per decade. And those 20 dB per decade factors correspond also to 6 dB per octave, where an octave is a doubling of the frequency. And we also saw that we could approximate the angle curves with straight lines. So Bode's method here says we can do this by hand. You start with real poles and zeros on the, so they're on the sigma axis, and there's nothing at the origin. And so here's our transfer function with the poles, zeros of beta 1, beta 2 up to beta m, the poles alpha 1, alpha 2 up to alpha n, and we factor out all the pole and zero locations. So we get a term out front, which in this case, when there's neither a pole nor a zero at the origin, turns out to be the DC gain, because that's just what you would get if S went to 0. But then you have these terms, the pole and zero terms are the form 1 plus S over corner. So when you go to do 20 log base 10 magnitude h of j omega, you've got a constant there that's just 20 log base 10 magnitude h of j omega, h of j 0. That's the DC gain in dB. And now each one of the poles and zeros has the form 20 log base 10 magnitude 1 plus j omega over corner. So this is again, the DC term is just a constant for all omega, but let's see what these 20 log base 10 1 plus j omega 1 plus j omega over corner looks like. So when omega is a lot less than the corner frequency, then you're just going to get 20 log base 10 of 1, which is 0. And when omega is a lot bigger than the corner frequency, you're going to get omega is going to be, the gain is going to be 20 log base 10 omega over omega corner, which is just going to be a straight line that starts at 0 dB and has 20 dB per decade growth with omega over omega c. We know that at the corner frequency there's a 3 dB error, so we can put a little marker for there on that, and then the smooth curve will connect those and go through the correction. And you can basically have you can start your correction 1 decade below the corner frequency and end it, actually you can do it less. You can see that actually the correction starts somewhere in between a decade below and ends someplace before a decade above. Okay, the angle curve we can treat the same way. For very low frequencies, which now means more than a decade below the corner frequency, then the angle is approximately 0, just the angle of 1. For very high frequencies, which now means more than a decade above the corner frequency, then you're going to get the angle, which is just going to be j, and that's 90 degrees. And then a straight line in between from 1 decade below to 1 decade above. The actual curves are off 6 degrees at a 1 decade below and 1 decade above. And so you actually have to start your correction here a decade below, 2 decades below the corner frequency, and it ends up 2 decades above the corner frequency. So, but you can still make the correction. You see it's a little bit funky compared to the gain curve because you're 6 degrees above, and then you actually want to go below the curve and go through the 45-degree point with a bigger slope than the actual straight line asymptote there, and then you come back through the 6-degree below, and then you're up to 90 degrees. So how do you do this when you've actually got something with multiple terms? So you got, here's a 0.1 s plus 1,000 over s plus 10. So the zeros at minus 1,000, the poles at minus 10. We factor out those values, so 1,000 in the numerator and 10 in the denominator. That gives us the DC gain of 10. If we plug 0 in here, we just get 10 for the DC gain. And then we have these terms of the form we said we needed the terms in. So 1 plus its s over 1,000, 1 plus s over 10. So for each of magnitude and angle, you just graph each one of these terms separately, and then you add them up, because you can add, since they're logarithms of products, you can add them up. So here's h as j omega, 10, 1 plus j omega over 1,000, 1 plus j omega over 1 plus j omega over 10. So first we mark off the frequency axis in decades of corner frequencies. And so luckily they agree by factors of 10 here. So we've got a corner frequency of 10. So we have 1, 10, 100, 1,000, etc. And then we mark off the vertical axis in increments of 20 dB. So 0 dB. And it's often convenient, just as a point of reference, if you do have powers of 10 in the problem you're working, to put the vertical axis through the line, through the point omega equals 1, and put the 0 dB horizontal axis through the horizontal axis through the 0 dB line. But you can actually put them arbitrarily, right? Then we'll draw the graph for each term. So here's the 20 log base 10 of 10 is 20 dB. Here's 20 log base 10 of 1 plus j omega over 10. That comes out to the corner frequency. It's a straight line at 0 dB until you get to 10 omega. Omega equals 10 radians a second, and then it rolls off at 20 dB per decade. And now this curve is going to be a straight line until you get to omega equals 1,000, and then it's going to corner up at 20 dB per decade. And then you sum these to get the asymptotic approximation of the frequency response. So here's a 20 dB gain in the low frequencies, decays at 20 dB per decade down to minus 20 dB per decade gain. So it's got a gain of 10 in high frequencies, a gain of 0.1 in low frequencies, and it connects between the two smoothly. And so you make the 3 dB corrections at each of the two corners, and then you draw your straight line between those. You do the angle curve the same way. You draw the, you mark off the frequency axis in decades. You mark off, I usually put angles, 45 degree increments or something, because we're going to have the 45 and 90 degree points that we're interested in. And so here's the angle of 10, which is 0. Here's the angle of 1 plus j omega over 10, which starts, again, we start a decade below the corner frequency of 10, go down to minus 90 degrees a decade above, and then make it minus 90 degrees above that. And the part associated with the 0, so it's 0 degrees out to a decade below the corner at 1,000, up to 90 degrees at a decade above the corner at 10,000, above the corner at 1,000, a decade above it at 10,000. And now connect the lines. So straight line sums add up just by adding up. And if you add up the slope of one, where you have a slope of a positive slope and the negative slope, they add up to a 0 slope, etc. Just like we did before, or we will do in a minute. So and then you put in your 6-degree corrections. Okay, so both the blue curve and the green curve would need a 6-degree correction. So this one's a correction of 12 degrees here. And then at 10,000, you have another 6-degree correction. And then you make a smooth curve through these. And so there's a smooth curve through those. And that's the actual angle curve, plotted versus log omega. And you say, well, it's kind of hokey to do this, right? But you look at what MATLAB does. And so here's the MATLAB plot of the same thing. And here's the Bode asymptotes. So you can do it by hand. You can do it by MATLAB. The reason to do it by hand is to know whether what you get when you do it by MATLAB makes sense. So when you have a polar 0 at the origin, it's a special case. You have to just say 20 log base 10 of j omega, like you're going to get here in the numerator, is just a straight line that goes through 0 dB at omega equals 1. So that's another reason to mark off the vertical axis at a horizontal argument of 1 radian a second. So here's minus 100. We factored out minus 100, so there's the gain minus 100. It's got a minus 40 dB. We have the pole at 100, so it comes out at 0 dB until 100 and then corners down at 20 dB per decade. And now the 20 log base 10 j omega is just going to be a straight line through omega equals 1 with a slope of plus 20 dB per decade. We add those up and get the asymptotes, put the 3 dB correction in, and then there's the actual straight line curve that goes through those. Do the same thing for the angle curve. Mark off our horizontal axis, mark off our vertical axis. Angle of 1 over 100 is 0. Angle of 1 plus j omega over 100. Straight line 0 degrees up until a decade below the corner frequency at 100. Straight line down to minus 90 degrees, a decade above the corner frequency at 1,000. And then, a decade above the corner frequency at 100, which would be 1,000. And then minus 90 degrees above 1,000. And then the angle of j omega is just 90 degrees because it's just the angle of j. Add those up. So it's a straight line, 90 degrees up until a frequency of 10, down to 0 degrees at a frequency of 1,000. 6-degree corrections, and then smooth line between them. And there's your actual angle curve. And this is what we saw earlier. So to summarize, Bode's method lets you use straight line approximations for the magnitude and angle to sketch the Bode plot. And we had, if you had a polar 0 at s equals minus alpha, 20 log base 10 of the magnitude of 1 plus j omega alpha is 0 dB below the corner frequency, a straight line with a slope of plus or minus 20 dB per decade above the corner frequency, where it's plus if that's a 0 and minus if that's a pole. The angle of 1 plus j omega over alpha is 0 degrees until 1 decade below the corner frequency. It's not plus or minus 9 degrees after 1 decade above the corner frequency. And then it's a straight line between 0 and plus minus 90 degrees 2 decades around the corner frequency. So, and it's plus if that's a 0 and minus if that's a pole. And then when you had a polar of 0 at s equals 0, you have the gain in dB as a straight line through omega equals 1 and 0 dB with a slope of plus or minus 20 dB per decade, plus for a 0, minus for a pole. And the angle is plus or minus 90 degrees, whereas plus for the 0 and minus for the pole. So next we're going to do the step response, go back to step response and see how transfer functions with different frequency responses, what you can learn about their step responses from the from the frequency response, and how you might make some trade-off decisions when you're selecting a better way to implement something or the kind of attribute you're willing to accept in the step response from what you know about the frequency response. So this has been EE300 Linear Circuit Analysis 2, Module 3, Video 6, Bode's Method of Plotting the Frequency Response.